All right, what's the difference between a type 1 and a type 2 error? So here, I think these are some interesting examples to kind of reinforce it. So a you can think of a type 1 error saying you're telling this man, hey, you're pregnant, which would be really bad. And then a type 2 error is an example saying, hey, you're not pregnant, she is. So this is when you're, a type 2 error occurs when you um, say there's no difference when in fact there really is. And that typically has to do with study power. And then a type 1 error is when we find a difference, but in reality there really isn't any difference or relationship. So, so if we look at this table here, we have truth about the null hypothesis in the population. So this is really what's occurring, and this is what we find. So if the null hypothesis is true and we accept the null, then it's correct. Whereas if we reject the null, but in fact it's real, that's when we observe a difference when none exists. If we are incorrect and we falsely reject the null hypothesis, we accept the null saying that there is no difference when in fact there is, we commit a type 2 error. And then if we reject the null and that's in fact correct, this is here. So if a researcher accepts the null hypothesis and it's true, they made the correct decision. If the null hypothesis is false, but he accepts the null saying there is no difference, this is a type 2 error, and it's 1 minus power, meaning we take about a 20% risk that that can occur. A type 1 error, which is much more significant, we usually set that only at 5%, or p of 0.05. So if we reject the null and say and that is a correct, in fact, true statement in the population, we are correct there. So we have what's these error terms. So we have an alpha error and a beta error. The alpha error is what we typically set at, say, a probability of 0.05 or a p of less this that significant will accept significant findings if they're less than excuse me 0.05. This means 5% of the time the difference is going to be due to chance, and we're willing to accept that 5% risk. Beta error is usually set at 0.2 or 20%, which means 20% of the time we're willing to conclude falsely that there is no difference, meaning that we would accept the null hypothesis. So you're probably asking yourself, well, why are there differences in these rates? Why aren't they the same? Well, because rejecting the null hypothesis means we might implement a new therapy incorrectly that in fact has no effect or that could be harmful. An example of this may be back from the days, some of you may be familiar with the COX-2 inhibitor, the Vioxx studies, which later on they found had some significant adverse effects. And when they found that preliminary studies, they found it had good effects on pain control, but later on they found some problems with it. In contrast, committing a type 2 error means we might only delay implementation of a new therapy because we didn't find a difference in them. But in fact, it really does work. So power is based on three things. The power of a study is based on the sample size, the effect size, and the p-value or the p-levels, what they call it here. Effect size represents the size of the difference or association or relationship or the magnitude of the treatment effect between the groups. Here's an example of when you're using a effect size for a continuous variable for a mean, you would take the mean in the experimental group minus the mean in the control group and divide it by the pooled standard deviation. That's how you calculate the effect size. Now, each statistical test has a slightly different method for calculating effect sizes. So Cohen's d is the most common effect size, which is used for continuous variables, where I just talked about the mean of group 1 minus the mean of group 2 divided by the pooled standard deviation across that sample. And here you can see they go through some estimates of how you would actually calculate that. So they go through this example. You have a mean difference of 4, and you have a pooled standard deviation of 4.53. So this actually, in fact, reveals a large d, or a large effect size, that tells us that these two differences between these two groups is large enough and consistent enough to be really important. So a d of 0.88 is rather large. Here's a quick guide to a choice of sample sizes for Cohen's effect size. Cohen was a statistician who developed these years ago. And these are some general rules of thumbs that we can look at. And these sample sizes will guarantee between 80 and 90% power to detect the given effect sizes. You can see here's some formulas. I'm not going to go over those with you. So you have small, medium, and large effect sizes. This is with an unpaired t-test. This is meaning you're looking at a difference in means between two groups, with a 0.2, 0.5, and 0.8 being the cutoffs. Here we can see the sample size. So a sample size for a small effect size here, we would need 400 subjects, or 201 in each group, to detect a small effect size on a continuous variable. In contrast, if we have a large effect size, we only need 28 or 14 per group. If we're looking at correlations, its cutoffs are 0.1, 0.3, and 0.5. Same thing. A very small correlation we're looking for, you would need 800. In contrast, for a large effect size difference in correlations, you only need 32. If we look at a 2x2, say a contingency table, same thing. You can see it's very similar at 0.1, 0.3, and 0.5. So like say a 10% difference, a 30% difference, or a 50% difference would be small, medium, or large, and those are cutoffs. Same thing. To detect a 10% difference, you might need 800. Whereas with say a 0.5, mainly only 32. Here's another table to keep handy that you can refer back to, which I've just brought over. Added a few other of the common statistical tests we've talked about in this course. The ones that I've added on here for you are the F-test effect sizes, 0.1, 0.25, 0.4. R-squared from a multiple regression, you can see those values here. A chi-squared, this is the 2x2. When you're looking at differences in frequencies or proportions between groups. And then odds ratios, this is something that you will see quite often in the anesthesia literature. And here what I found was an odds ratio of 1.5 is small, a medium is 3.5, and a large effect size odds ratio would be 9. So what are the three factors that impact a power analysis? Sample size, effect size, and the p-value. What are the three factors needed to determine a sample size? You need to know the effect size, the alpha error, or the p-value, and the power. And how do we estimate effect sizes? Well, investigators, many times, this is a priori, meaning we're doing this before we're collecting our data. And we do this by estimating it from the best available prior knowledge and evidence. Sometimes we may conduct pilot studies. Investigators may do this. I've done this before to estimate an effect size. We may look at more commonly, we look at similarly published studies to the one that we are proposing and estimate effect sizes. Sometimes it's just really our best guess and a hunch. We're not always perfect. Sometimes we miss the mark. You also have to ask yourselves, how much of an effect size, how large are we looking for? We have to think about that, and that has to do with what you're interested in studying, what your hypothesis, and what is clinically relevant, or what is one that you might expect to find. Also, sometimes when we're looking at effect sizes, we got to look at feasibility. So sometimes we may decide to take a slightly larger effect size because we just don't have enough money to collect, hundreds and hundreds of patients. There's multiple decisions that are made in research that can certainly impact the findings from a study. All right, we're going to pause the video there and then restart with some examples of power analysis and effect size.